Hey guys, so in this video I'll show an end-to-end demo of the RedSan tool in action. So in my previous presentation video I talked about the theory and concepts of how the RedSan tool works, and I also linked this video in the description of the previous video. So we are going to run the RedSan tool on a program called 2mm, which is inside the Polybench GPU. It's an open source benchmarking tool. So first we are gonna download or clone the Polybench GPU repo. Yeah, once we clone the repo, we can see the 2mm program lives under the CUDA directory. We open a terminal here, and firstly we are gonna compile it with NVCC using the optimization flags, and then we are gonna profile it with NCU to get a baseline benchmark. So that's what we are doing here. Yeah, after compiling the 2mm, we use NCU and use the set full parameter to get all the metrics. As you can see, it profiles both the kernels. It shows us the GPU time in seconds. Then we use this, then we open this NCU report inside the NCU application, and we just write down the baseline benchmarks. The two parameters or metrics that we care about are the total cycles and also the total memory instruction count. So for this 2mm program, we can see the total cycle count is around 36 million, and that can differ from GPU to GPU, so it'll be less or more on different GPU hardware. Then we use this search tool to search the global load and store count for the memory instructions. So the global memory load count is around 67 million and global memory store count is around 33 million. We are doing the same process to get the store count as well. Yeah, as you can see, it's around 33 million. So our total memory instruction count becomes approximately 100 million. Once we have that, we save that document, because at the end after we have run the RedSan tool, we'll come back to this document and see the improved performance and note that down as well. Now we are inside the directory where we downloaded the RedSan Docker image. We are opening a terminal here, and we are using the commands that are given in the paper itself. First, we are checking what images we have. Once you have loaded the image into the Docker, you'll see the RedSan AE latest image, and then you run it using this command, and you also give it full access of the GPUs. Here I'm opening this Docker container inside Visual Studio so we can better inspect all the files, and if we have to make any changes to any files, it's easier to do so. You can just look it up how we can connect Docker containers in VS Code. Once this container loads up, we'll be able to see all the directories inside it Currently it has 3 directories called AE programs, AE scripts and RedSan. As you can see, you don't close this shell terminal that you loaded the image in and ran the image in. You keep that open, and inside this VS Code terminal will do the rest of the installation and the running of the RedSan tool. First, we are just switching to a RedSan directory inside which there is a binary directory called bin, inside which we'll find our installation script. Yeah, as you can see, this is the script that we care about, the install release sh. We just run this script with the source keyword, and yeah, that should start the installation of the RedSan tool. It'll take around 10-15 minutes. It has like around 22 processes that it does, and yeah, after that you can see it installs everything in the RedSan install directory. Once that is done, we use the next command to switch into the AE scripts directory, and inside that we have to run this script called setup benchmarks. It basically compiles all the benchmarking programs that RedSan provides. It provides a bunch of programs. We actually don't need to compile all of them, but it just makes it easier and streamlined to do that, and it only takes like around 10 minutes. Once that thing is done and all the programs are compiled, we head over to the AE programs directory where there will be like the Polybench CUDA 2mm program, which will be already compiled with the optimization flags. So we'll have the optimized binary there. Then we copy this script from the RedSan bin directory called example run.sh, and we paste it into the target directory inside which our 2mm program lives. Once we do that, we have to open it and update this last line and put the actual name of our program, which is 2mm.exe. After doing that, we can run this example run.sh using the source keyword. Once that is done, the RedSan will generate 2 files called instructionaccount.csv and log files. We download both of them locally so we don't lose it when we close the Docker container. Now let's open that .csv file, which has the actual redundant program instructions. As you can see, it mentions all the program counters which make memory accesses, and the program counters which have redundancy rate of greater than 0 are the ones that matter. We copy this kernel ID and then open the log files. Inside that, we'll just search for that kernel ID, and that will give us the base program counter that RedSan assigns to this kernel. It's under this line here. We copy this base program counter, base memory address. We do the same for the second kernel. From the CSV, we first copy its ID and then we search it into the log files. That's the second kernel's ID. Here we find the function program counter, base program counter that was assigned to the kernel 2. Once that is done, we'll open the NCU and first we'll calculate the offset. Now we open the CSV again and we go to the program counter, the line which has the first redundancy, and we look at that PC address, which is something like 7AC and ends with 90. We take that address and we can't use it directly inside NCU because NCU uses this offset functionality. So that's what we are calculating here. As we can see, we are subtracting the base program counter for kernel 1 from this first redundancy program counter. And you can use this online tool called hex calculator to do this subtraction. Yeah, the subtraction is around 290, which is our offset that we'll use inside the compute to find the actual source code line inside our program. So as we can see here inside compute, we go to the source tab and here we take the first first line's address and we add the offset to it using the same tool. So we get the actual instruction line. It's kind of cumbersome, but I think these must be the limitations with the software. But yeah, it still works correctly. When we add our offset to that address, we get the actual address of our source code line where the redundancy exists. As you can see, it's this line which maps to the line inside the for loop in which we are using this temp variable. Yeah, it matches perfectly with that address. So we know that's the line that has the memory redundancy. Once we know that, we can use different techniques to optimize that specific line. We can use either the restrict keyword to optimize the memory access there, or we can use like a temporary register variable to store the temporary calculations inside the loop and not use a loop invariant. And outside the loop, we can then set the temp to that temporary register. So that's what we are doing here right now. For both the kernels, we'll do the same thing. So we declare a temporary variable called ACC, which is like an accumulator. And inside the for loop, we use that variable which will be living on a register, which is the fastest memory access that we can do. And we do the same thing for the kernel 2 as well, because that also has the same issue where we are doing an unnecessary memory access inside the for loop where there exists a loop invariant. This I plus NL plus J never changes inside the for loop because for loop depends on the K variable. So we again declare a variable called accumulator. We set it to the value that the D, I, NL, J was using, the same multiplication. Then we use just that accumulator variable here inside the loop, which is much faster. And that's it. Those are the only two changes we had to make to improve the performance of this program like massively. Now we'll compile this program again with NVCC using the optimization flags, and then we'll profile it again with Nsight Compute, and then we'll see like if there was any actual improvement in the performance. Now we are using the same NVCC command here to compile this modified 2mm program. We are using line info because that gives us the mapping, source code mapping. We do that, then we run this NCU set full command that gives us the report that we can use open inside the NCU software. Yeah, the report is generated, and now let's open it inside NCU. As you can see already in the cycles section that the cycles have decreased significantly. We were previously at 36 million cycles and now we are around 11 million. So we are just logging our improved metrics. There's some difference between the kernel 2 and kernel 1 for both the metrics, but they are like minimal, so we can approximate them to a number like 11 million. Now we use the same search method to search the global memory load and store count. As you can see, the load count remains the same, around 67 million, because the redundancy we had was with the store that we were doing. We are doing unnecessary stores inside the for loop. And as you can see, the store count has gone down significantly. Previously it was around 33 million, now it's only around 32,000. I made a typo here, it should be around 67 million, which I do correct later in the video. So our memory count was reduced by around 33 million, which is significant. So now we can see side by side that we were able to reproduce the exact results from the paper, and that should conclude our demo. Thank you.